In this video, I will address the remaining issues from my previous videos. Firstly, I will discuss the scaling of pixel values in PyTorch for our MNIST example. Secondly, I will clarify the dimensions required for calculating log softmax. Thirdly, I will explain why the TensorFlow model I coded still worked without specifying the input shape for the flattened layer. The fourth issue will be covered in a separate video. And finally, I will explain the concepts of training, validation, and testing. In machine learning, image classification often involves scaling or normalizing pixel values. For instance, in the MNIST dataset, image scaling in TensorFlow is straightforward. However, in PyTorch, many tutorials do not explain why the values 0.1309 and 0.3084 are chosen for normalization. Let's analyze the following code to understand the rationale behind these values. In this example, we load the MNIST data without applying any transformations. The data is converted to float type, and statistics such as minimum, maximum, mean, and standard deviation are computed. By scaling the mean and standard deviation, we arrive at values close to 0.1309 and 0.3084. The command we encountered before tells us to normalize the image data to have a mean of 0.13093 and a standard deviation of 0.30845. Let's do some simple math. Pause the video to understand the formulas. Based on the last formula, the following code may be what PyTorch does when performing our normalization. Let's address the second issue by examining the demo code. After importing the necessary libraries, we define a 2D tensor named x. We then apply the sum function to the tensor by specifying the parameter dimension equals 0 or 1. When the dimension parameter is set to 1, the summation is performed on each row. When the dimension parameter is set to 0, the summation is performed across rows. Initially, when I learned TensorFlow and PyTorch, I found it confusing to understand the shapes of the input, hidden, and output variables. I automatically assumed that the output at each layer was one-dimensional for the architecture shown here. However, the first dimension actually represents the batch size. Let's consider another example. We first define a 2D tensor named logits. We then apply the sum function to the tensor by specifying the parameter dimension equals 0 or 1. To understand how softmax is applied to the tensor, we define a custom softmax function and apply it to each row of the tensor, comparing the results with the PyTorch version of the softmax function. Next, we apply the softmax function to each column of the tensor and compare the results again. In summary, when dimension equals 1, softmax is applied to each row of the tensor. In neural network training, batches of samples are used as basic units for training. Therefore, for the output layers, the first dimension typically represents the batch number. Let's address the third issue by examining the following code. This is the initial model I built, and I mistakenly positioned the input shape in the hidden layer. When attempting to get a summary of this model, an error occurs, indicating that we need to build the model before we can obtain a summary. As expected, the build fails because the system requires the input shape. The corrected model does not have this issue. The lesson we learned is when using the TensorFlow Sequential API for model building, the input to a layer is inferred from the previous layer, so we must provide the input shape for the first layer. The batch size is currently unknown. The second dimension reflects the structure of our MNIST model. For fully connected networks, calculating the number of parameters is straightforward. I am very curious about how the model worked without the input shape specified for the flattened layer. For clarity reasons, I renamed the model to Model 2 and restarted the session. The model was successfully compiled, trained for one epoch, and after training, we obtained the model summary. The default batch size is 32. It seems that after the dataset is provided, the input to the first layer is inferred. Let's address the fourth issue. Since concepts like entropy and cross-entropy can be difficult for laypeople to understand, we will create another video to explain this topic. Here, I want to explore why the more intuitive error measure, mean square error, is not commonly used for image classification tasks. This is the TensorFlow code I used before, with minor modifications for the current purpose. The key change is using MSE instead of cross-entropy as the loss function. Training the neural network improves performance, but it does not match the performance achieved with cross-entropy as the loss function. Why is this the case? I will attempt to answer this question, but I still do not have a definitive answer. So far, we have considered neural networks as complex functions with multiple parameters. These parameters are fine-tuned through training on datasets to enable the models to generalize effectively to new data. Is there an optimal approach to identifying the best model for a particular task? There is no definitive method for selecting the best model for a given task. Models are typically developed based on biological systems or created from scratch. To determine the most effective model, a process of experimentation is necessary. This involves validating and testing the candidate models to assess their performance and suitability for the task at hand. In most supervised machine learning tasks, it is recommended to divide the data into 3 sets: a training set, a validation set, and a testing set, each serving a specific purpose in the model development process. Training neural networks can be computationally expensive in real applications, so it is crucial to monitor the performance of the neural networks during training to detect overfitting in real time rather than after training. This allows for the training process to be stopped if overfitting is detected. The validation set is specifically used for this purpose. The testing set is reserved for evaluating the final model's performance. This data is unseen during training and validation, providing an unbiased assessment of the model's ability to generalize to new data. I will use the MNIST example to demonstrate how we perform validation and testing in the next video.